In the next several videos, we're going to focus on three different related functional groups. Those are carboxylic acids, carboxylate salts, and esters. In this video, we are going to introduce each of those functional groups, including some of the important applications of molecules that have these functional groups, and we're going to look at how we can recognize each of these groups. By the end of this video, you will understand how all of these seemingly unrelated images tie together under the theme of carboxylic acids, carboxylate salts, and esters. Let's go ahead and take a look at these functional groups that we'll focus on here, starting with carboxylic acids. In the next several videos, we will look at naming molecules that contain each of these functional groups. We'll also look at important biologically relevant reactions that these undergo that will help us understand in later chapters lipid structures, lipid functions, and a variety of other biologically relevant molecules as well. Starting with carboxylic acids are required to have a COOH group. We see in this molecule here, this group that I'm circling in pink is our group that's required for the molecule to be referred to as a carboxylic acid. If we want to just refer specifically to the COH group, I will refer to that as a carboxy group. The R group here can represent a carbon chain, it can represent a ring of carbons or an aromatic ring, or really whatever else we want to fill in here. We would classify this group still as a carboxy group of a carboxylic acid. The next group that we will focus on is a related group referred to as a carboxylate salt. As we will learn in a later video, the way that a carboxylate salt forms is by deprotonation of a carboxylic acid. So when a carboxylic acid is placed into a solution with a relatively high pH, this hydrogen atom, this proton from the carboxylic acid, is easily lost. And the product that results from losing this proton of the carboxylic acid is the so-called carboxylate salt. So you will see in the carboxylate salt that the difference between it, the carboxylate salt on the right, and the carboxylic acid on the left is just the loss of this proton here. The proton is lost, and once that proton is broken away, we're left with an anion here. That anion needs a cation to counter it, which is a metal of some sort. So I'm going to put M plus here. And that M, the metal, is a group 1 metal from the first column of the periodic table. So that could be sodium, for example, lithium, potassium, etc. And we refer to this as a carboxylate salt. Carboxylate coming from the fact that it has the COO group, and the salt part referring to the fact that this is not a molecule that has no formal charges anywhere in it. Instead, it's a salt because it has a cation and anion present in the molecule. So that's why we refer to it as a salt, much like NaCl is a salt that has Na plus Cl minus. Salts in general, in a broader sense, are just defined as compounds that have positive and negative charges present. And so that's why we call this a carboxylate salt. So carboxylic acids and carboxylate salts are very, very related in that we will be taking carboxylic acid salts, raising the pH of solutions to result in deprotonation, loss of this proton, to give the corresponding carboxylate salt. On the other hand, if we lower the pH to make the solution more acidic, we can go back in the other direction to convert a carboxylate salt into a carboxylic acid by creating an environment that is rich in protons, so there's plenty of protons around to create this carboxylic acid. We will see later in this unit, in future videos, how creating carboxylate salts from carboxylic acids can be important in things like the food manufacturing industry and creating molecules that have improved water solubility over the starting carboxylic acid. A third functional group that we will focus on in this chapter that is related to the carboxylic acids and the carboxylate salts is an ester. An ester, like carboxylic acids and the carboxylate salts, has the carbonyl group directly bonded to an oxygen. In addition to that, rather than having this oxygen be an oxygen anion or be an OH group, Instead, this becomes in an ester an OR group, where R is an alkyl chain or an alkyl ring. It's going to be an alkyl group of some sort, in other words. And that is what is required for this to be referred to as an ester. So when you're looking for an ester, be looking for carbonyl directly bonded to oxygen. That oxygen has some additional carbons attached to it. That could even be an aromatic ring here, but it's not an OH group, and it's not an O negative group. It's not an oxygen anion. So this is going to be our ester functional group. So by the end of this chapter, you'll be proficient at naming molecules that contain each of these three functional groups. You will also understand reactions that allow us to convert between any of these three types of functional groups that are closely related. And that's why we're covering them all here in this same chapter. Let's take a look at some of the applications of these molecules, going back to some of those images that we saw on the starting screen. These functional groups are very, very common in a huge variety of food products. They're also produced biologically by the human body and other organisms as well. One example of the importance of these functional groups in food is a common preservative called sodium benzoate. In this beverage, you will see sodium benzoate listed here within parentheses as a preservative. And sodium benzoate is very, very commonly used as a preservative in a variety of foods. In fact, if you look in your pantry, you will find undoubtedly sodium benzoate present in the labeling on some of your food items. The structure of sodium benzoate is an aromatic ring directly connected to a COO group that has sodium bonded to that oxygen, hence the sodium part of sodium benzoate. This is the structure of sodium benzoate, and we should be able to identify which functional group this molecule has based on the information from the previous slide. This particular molecule contains a carboxylate salt because of the fact that we have a COO minus group right here connected to a sodium. And we recognize, even though we don't put O minus and an A plus here, that it is implied that there's a negatively charged oxygen and positively charged sodium because there is a huge electronegativity difference between the two atoms. Sodium, if we take a look at the periodic table, is in the far left. Oxygen is closer toward the right side of the periodic table, meaning there's a large electronegativity difference, and hence this is an ionic bond, making this a so-called salt. What about some other examples of molecules that we can look at that apply this information? So compounds such as common arthritis relief agents and other pain relievers contain a compound called methyl salicylate. Methyl salicylate is an example of an ester. The particular structure of the ester that makes up methyl salicylate is as follows. We have an aromatic ring. That aromatic ring is directly bonded to a carbonyl group that's bonded to an oxygen and bonded to a methyl group here at the end. Remember that if you have a line here, it indicates the end of that line represents a CH3 group. And then additionally, at the ortho position, one spot over in the aromatic ring, there is a hydroxy group. This particular molecule, in taking a look at it, we would recognize of the functional groups that we have discussed in this particular video that this molecule contains an ester functional group because of the fact that it has that required carbonyl group directly bonded to an oxygen and directly bonded to an alkyl group there. So I've circled in red here what constitutes our ester group of this methyl salicylate. Methyl salicylate also is known in a variety of other applications as well. In addition to the analgesic pain relieving properties that it plays in creams such as this arthritis hot cream, it also gives a minty flavor and fragrance. So if you've used products that have sort of a wintergreeny flavor or fragrance, chances are that's caused by methyl salicylate, which is produced synthetically in an organic chemistry lab. And a bioidentical form of that is produced by a variety of plants, such as the wintergreen plant as the hallmark of that. Now, another very, very common example of a substance that contains a carboxylic salt, an ester, or carboxylic acid is vinegar. The active component of vinegar that gives it its sour taste is a compound called acetic acid. Acetic acid is a 2-carbon carboxylic acid, and like other carboxylic acids, acetic acid has a sour taste. The acid group in this is what generally gives it the sour flavor properties. Now here's another really cool example of a multifunctional compound that fits into these functional group categories, and that is a compound called butanoic acid, or as the common name, butyric acid. And you may be saying to yourself, why in the world does she have a picture of a person sweating and a picture of some butter or cheese here in the same frame? That is because butyric acid has multiple roles. One is that butyric acid is one of the components that is in sweat, and is why sweat has kind of a characteristic sort of sour or unpleasant smell. Butyric acid is also interestingly found in a variety of cheeses and butters, and gives the cheese or butter its characteristic flavor property. The structure of butyric acid, or butanoic acid as it can also be called, is a 4-carbon carboxylic acid, like so. No branches coming off of it, nothing fancy, just a 4-carbon carboxylic acid is what gives the sweat its kind of characteristic, somewhat unpleasant odor, and at the same time, in a different concentration, is able to give cheeses and some butter its characteristic flavor. Salicylic acid is another example of a common carboxylic acid that has practical applications. Salicylic acid has our COH group right here. Adjacent to that is the hydroxy group, and the common name for this structure is salicylic acid. You will notice that the structure of salicylic acid is analogous to methyl salicylate, where the difference is that the carboxylic acid group has become an ester group through a simple chemical reaction to convert between these two molecules, and we will learn about that type of chemical reaction later in this chapter. Salicylic acid and methyl salicylate have pretty different applications. Salicylic acid is commonly used in facials and skin creams as an exfoliant to remove the top layer of skin. It also acts as an anti-acne treatment in a variety of face washes and face treatments, and you quite possibly have a substance with salicylic acid present somewhere in your bathroom. Finally, as an important and biologically relevant example of a carboxylic acid, we have GABA, which you may have heard of GABA, which stands for gamma butanoic acid, as an important neurotransmitter. GABA can also be referred to in the IUPAC nomenclature system as 4-amino, because of the fact that at the left-hand end of this molecule we have an NH2 group, 4-amino butanoic acid. And this represents an important substance that's produced biologically in the brain as a neurotransmitter. Now, with this variety of different esters, carboxylic acids, and carboxylate salts in mind, what we are going to do in the next several videos is look at how we derive the names of these molecules and what some of their reactions are that allow us to understand how these molecules are related in terms of their physical and chemical properties and functions, and also how they are distinct from one another in these aspects. Stay tuned for that.